A warm welcome to all present here. Today we'll be seeing the practice questions for week 8 content. So let me share my screen first. So in this session we'll be seeing some practice questions for the NPTEL course Advanced Concrete Technology. The course code is noc22 ce58. So today we'll be seeing some practice questions from week 8 content. So to the person who have joined new today, let me explain uh, explain how to give your answers and polls before starting the session. So here to the bottom right corner of your screen, there is different options. Out of that, you can find a triangle, square and a circle together called activities. So if you click that activities, you can find 4 different options. Out of it, if you click polls, you can find the questions launched. You can give the answers once we discuss the question. Okay. So once you give your answers, then I will be explaining the answers and then giving some explanation from the lectures as well. If you have any query, you can stop me and then you can ask your query. Okay, so mostly I'll finish the session 5 to 10 minutes earlier. So we'll have some time to discuss if you have any other query. So let me share my screen again. I'm Nilakanmani. I'm an NPTEL TA for the course Advanced Concrete Technology. I'm a PhD candidate from IIT Madras. So let's get into the practice questions for this week. So in this particular week, Sir has discussed about uh, um, how to design what are the new design philosophy in designing high strength concrete, and then what are the properties of fresh concrete. And Sir has also discussed about how to measure rheology, workability. So all these days you have just deal with to measure the slump of the concrete, and then we'll measure only the slump and refer to the workability of the concrete. But in this particular lecture, Sir has explained about how we can measure the uh, uh, actual parameters to measure the workability of concrete by using rheology measurement tools. Okay, now let me start read out the question for you guys. So please give your answer in polls. If you're not able to answer polls, give your answer in polls, you can use the chat box to give your answers. To the if you're using a mobile phone, there will be 3 dots, right? If you click that, you can find an option called activities, and then you can give your answer in the polls. Try to give your answer in polls. If not, please give the answer in chat box at least. Okay, now let me read the question and then start the timer. So, okay, first let me read out the question. The question 1 is, am I audible to all? Can someone unmute and say, am I audible?
Yes, ma'am.
Okay, thank you. At times if I ask some question, please answer, or else I have to come I have to close this page and I have to come back again to meeting, so that will disturb the class. Please respond. Okay, then only I'll get to know whether you guys are available or not. Okay, so the question 1 is, which is from the practice assignment questions. The yield stress and plastic viscosity are 2 important parameters in rheological behavior. I hope you guys know what is yield stress and plastic viscosity. So we have to say the yield stress is a measure of what, and then the plastic viscosity is the measure of what. So here you have 2 options to pick. Uh, uh, so you have to pick what is yield stress and what is plastic viscosity. There are 4 options out of it. Option 1 is uh, yield stress is stress required to stop the flow, and then plastic viscosity is the friction between the particles. And then option B says yield stress is the stress required to overcome to start the flow, and then plastic viscosity is the addition, is the measure of addition. And then option C, the stress required to initiate flow when the material is static, and then plastic viscosity is the measure of resistance to flow. And option D says both A and B. So now let me start the timer for 2 minutes. Please give your answer. In the meantime, if you're not able to follow the question or you have any query regarding the question, you can stop me by any time and you can unmute and ask the question. If you're not able to speak, you can post the question in the chat box. Time is up. Let me stop sharing the screen and see your response. Okay. Okay, option C. Okay, there are around 3 people in the class, but only one has given the answer and one has given the answer in chat box. Do you guys find it difficult to give the answer? Okay. Once again, I'm repeating, to the bottom right corner of your screen, there are different options. Out of that, you have to click activities. If you click activities, there is option called polls. If you click that, you can find the questions already launched. Or else you can, there is 3 dots here, right, for more options. If you click that, you can find that in your mobile phone, if you are logged in from your mobile phone. Okay. Or else give the answer at least in chat box. Okay. So now let me end the poll for question 1. I hope from question 2 you guys are ready to give the answers. Okay. So let me get back to the PPT. So here is the answer. So this is snaps from the, these are some snaps from the lecture PPT. So here in the slide about shear yield stress, they have mentioned minimum stress needed for the flow to initiate. So the cement paste or cement concrete will be will be at rest. Okay, it will not be subject to any motion. So initially it will have more resistance to flow. So we'll find out what is the minimum stress needed to flow, needed for the flow to initiate. So that is a shear yield stress, and from rest to flow. So how much it like we are finding the minimum stress that is required for the flow to initiate. That is the yield stress, and then coming to plastic viscosity. So while flowing is about rest to flow, and plastic viscosity while flowing, how much resistance the paste is uh, having while flowing. That the resistance to the flow is nothing but the plastic viscosity. Okay, so the correct answer is option C. Stress required to initiate the flow when the material is static. That's nothing but rest. That is nothing but the yield stress. And then plastic viscosity is the measure of resistance to flow. So while flowing, how much resistance the paste is providing, is having. That is that is nothing but the viscosity, plastic viscosity. I hope you guys got it right. So now let's move to question 2. I've already launched this question in polls. Please give your answer in polls, or else at least give your answer in the chat box. Okay. So now let me read the question for you guys. The question is the formula for maximum density gradation proposed by Fuller. So he has proposed a gradation based on maximum density. So you have to find out the correct formula. Okay. So where PI is nothing but the passing sieve size DI. DI is nothing but the sieve size, and PI is nothing but the percentage passing through the sieve size DI, and capital D is nothing but the Maximum size of aggregate. Okay, there are 4 options. Please pick the right option. Let me start the timer now for 2 minutes. Please take your time, read out the question again, and then you can give your answer. Do someone want me to post the question in chat box? If you want, please unmute and tell me. Let me post the question in chat box as well. Time is up. Has everyone given the answer? Okay, let me stop sharing the screen. Okay, only one person has given the answer. Okay, so what about chat box? Oh, no one has responded here. Okay, there are around 4 people in the class and only 1 out of 4 has given the answer. What happened to the others? Do you guys find the question is very difficult? It's already posted in the practice assignment questions for week 8. I already have gone through the question. Okay, fine. So now let's move to the solution part. So here from the maximum density criteria slide, it's already given. In 1907, Fuller proposed the formula for maximum density gradation. The formula is nothing but Pi is equal to 100 into di small di divided by capital D, that is nothing but the maximum size of the aggregate. So Pi is the percentage passing, C says small di. Okay, di small di is nothing but the CF size. So this is the formula for the maximum density gradation proposed by Fuller. Okay, now let's move to question 3. Question 3 requires active participation from the class for sure, or else it's not going to move forward. So I have just taken this slide, this particular image from the lecture PPT. So I've just given 1, 2, 3, 4 for different rheological models here. So you have to find the rheological model. What is 1, what is 2, what is 3, what is 4. I can give you some options. One of the models nothing but uh, Newtonian model, Newtonian fluid, and then Bingham model is there. Shear thinning and shear thickening model is also there. So let me start the timer for 2 minutes now. Please write the answer in the chat box, not in polls. Please write the answer in chat box. Name it as 1, 2, 3, 4. If you have gone through the lectures, for sure you'll know the answer. Here the x-axis is nothing but shear strain rate, and then y-axis is nothing but the shear stress. Shear, so you have to find the correct rheological models, naming from 1, 2, 3, 4. At least for sure everyone should know what is 4 at least. What is the rheological model number 4? It's very simple. And then 2 is also a little bit quite simple, but 1 and 3 you have to be sure. If you have gone through the lectures, you know the answer. Time is up. Do you guys still need time? If someone needs time, please unmute and tell me, or else I'll stop sharing the screen and then I'll come back to chat box now. Okay, I assume that you guys have given the answer. Let me get back to the response, class response. Okay, only KPC Rao sir has given his answer. I could not find any other active participant from the class. What happened to the others? Okay, one is shear thinning, okay, Bingham model, shear thickening, and Newtonian model. Yeah, the answer is right. Okay. Do you guys watch the lecture videos and went through the lecture PPT? So before coming to the live session, if you're not going through the lecture PPTs and lecture videos, it will be really difficult to understand what I'm speaking. So please go through the lecture PPT, lecture videos before coming to the class. So then only you can actively participate in giving answer. So please try to give your answer in the chat box. At least everyone should know what is like option 4 is Newtonian model. You guys would have known it very it passes through the origin. It has a linear uh, uh, it has a linear relationship between shear stress and shear strain. So everyone knows what is Newtonian model, how Newtonian fluid behaves. So please try to give your answer. I know you guys know the answer, but you guys hesitant to write the answer in chat box. Please don't feel bad. So if you are not sure about the answer also, it's fine. We'll discuss. That's not an issue at all. Okay, now let me get back to class lecture to the next question. Okay, before going to the next question, we'll see the answers here once again. So here, this is the thing. I've hidden the names of the models from the lecture, and I've just posted the slide directly from the lecture. So here one is nothing but shear thinning. So let me come from Newtonian model, so it's very easy to follow. So it doesn't have any shear stress. That is, it does not. If you flow water, if you take water in a jug and put it, if you pour the water on the table, it does not show any resistance to flow. It just immediately flows, right? It does not like from rest to flow. It does not have any shear stress, right? It does not have any yield stress. So it passes through origin. It has a linear relationship between shear stress and shear strain. It does not have any so that is the thing. And coming here from Newtonian fluid, that's nothing but number 4, and 2 is nothing but Bingham model. In Bingham model, it is similar to more or less Newtonian model, but it initially has some shear stress. Once it starts to flow, it uh, it has a linear relationship between the shear stress and shear strain rate. Okay, so it initially shows some shear stress. So mostly we use Bingham model to model uh, cement concrete or cement paste. So it is one of the simplest model to model cement concrete. It doesn't have much parameters as compared to other models. It's very simple with one or two parameters. Now coming to 1 and 3, here you can see that there is no linear relationship between shear stress and shear strain rate, right? So here 1, you can see that with increasing uh, shear we can see that with increasing shear strain rate, the increase in shear stress is not evident, right? It starts to flat. The curve starts to flat here, which means why initially there will be some resistance to flow once you start mixing. It is more or less similar to cement concrete. So initially when you take a bucket of concrete, if you initially start to mix it with a wooden rod or a steel rod, so initially you will face more strain, more resistance to mix the concrete in the bucket. But once you start mixing continuously, once you start to move the rod in it, so you can move the rod easily. But once you put it to rest, again start to mix, then you will face some resistance. But once you start mixing it, you can move the rod easily. So this kind of behavior is this kind of similar behavior is observed in the cement concrete. So which is nothing but shear thinning. Increase in shear rate, the shear stress will not further increase. It tends to flat. And then coming to third option 3, it's nothing but shear thickening. So once you start mixing, when you increase the shear strain rate, once you increase the speed of mixing the let's assume if you have taken a cement concrete in a bucket, and you start mixing, this kind of behavior is not mostly observed. But if you add some viscosity modifying agent, so in self-compacting concrete, so we use more plasticizers to increase the flow of the concrete. So once you add some VMM, viscosity modifying agents, to reduce the bleeding property, because once we add more superplasticizers to the cement concrete, it tends to bleed at times. So we add some viscosity modifying agents to increase the viscosity of the cement concrete. So in such cases, when you increase this shear strain rate, while increasing the shear strain rate, you will feel more, you need more shear stress, the yield stress will be increasing further. So in such case, you will feel more difficult to mix the concrete at higher speeds. Okay, I hope you guys got it right. I don't want to explain it further because already it's explained in the lecture as well. So one is nothing but shear thinning. The shear stress will not increase further once you increase the shear strain rate. And then coming to number 2, it's nothing but Bingham model. Initially the fluid will have some shear stress. Once it starts to flow, there is a linear relationship between shear stress and shear strain rate. And then coming to third one, it's nothing but shear thickening model. And then so with increase in shear strain rate, the shear stress also increases. And coming to option 4 is nothing but the Newtonian model. The best example is water. Okay, now let's move to next question. Question 4 is very complex. It's directly from the practice assignment questions. So if you know, if you have understood question 3, question 4 is very simple. I am not able to load the complete question in polls. I've just entered the question here because there is limits to type the question in polls. So let me read out the question first and start the timer. So here they are saying 3 fluids. There are 3 fluids named A, B and C. Okay. So now they are explaining the behavior of fluid A. So fluid A starts flowing as soon as a pure shear is applied. Okay. No initial resistance is observed. I have just explained recently. So just you can now know the answer readily. So fluid A starts flowing as soon as the pure shear is applied. No initial resistance is observed. Okay. And the fluid A does not show any hysteresis and follows a linear relationship between shear rate and shear strain. Okay, it shows a linear relationship. And then, so now you got it, does not have any it does not have any initial resistance to flow. Okay, and the fluid B mimics the shear stress to shear rate behavior of fluid A. Possess a material characteristic in lieu of which a minimum shear stress is required to initiate the flow. So it has a linear relationship between shear rate and shear strain, but initially it requires a minimum shear stress required to initiate the flow. Okay, I have just explained the question. So question 3. So you guys would have known what is fluid B as well. So the fluid C mimics the behavior of fluid B when during the loading phase. They are saying that it initially requires some shear stress. Minimum shear stress is required to initiate the flow, as explained in fluid B, but changes to a lower yield strength during unloading phase. So how to, let me draw it here. So pen, okay. So if this is the, I'll assume that this is shear stress, and then it's nothing but shear strain rate, shear strain rate. Okay, it's nothing but shear stress. Okay, so it's nothing but shear stress, and this is nothing but shear strain rate. So here they are saying fluid A does not show any like it initially it is not, doesn't show any no initial resistance. So we are saying that does not have any shear stress. So it passes through origin and it has a linear relationship. This is fluid A. And then coming to fluid B, they are saying it mimics the stress to strain rate behavior of A, and which means it has a linear relationship, but it possesses a minimum shear stress, which is required to initiate the flow, which means it has some shear stress, and once it starts, it has a linear relationship between shear stress and shear strain. Assume these both are straight lines, okay? So, sorry, this in this image shows some it shows us a non-linear line, but it's a straight line, okay? And this is A, and then this is B. Just reading the question and drawing here. Please give your answer in polls or chat box, please. And then fluid C mimics the behavior of fluid B when during the loading phase, which means initially when we try to when we initiate the flow, when we try to mix the concrete or initiate flowing during loading phase, the behavior of the fluid C is similar to fluid B, which means it has some shear stress. Okay, assume that it has some shear stress, and then but changes to a lower yield stress during unloading phase, which means it has some shear stress, but when it comes to unloading phase, the yield stress decreases, which means the shear stress required to initiate the flow is there during the loading phase, but when during the unloading phase, the yield strength decreases, which means during the unloading phase it will have a lower yield stress. Initially it has more yield stress, and during unloading phase, once it tends to once we load, it has higher yield stress, and while unloading it has lower yield stress. This is the type of a behavior which is nothing but which we call it as hysteresis. So now you guys have to give the answer. Let me start the timer for a minute, and then we'll see the answer. Here there are 4 options given. One is first option says A is rheopatic, B is pseudoplastic, and C is Bingham fluid. And then option B says A is Newtonian, B is non-Newtonian, and C is shear thinning. And option C says A is Newtonian, B is shear thinning, and C is thixotropic. And option D says A is Newtonian, B is Bingham fluid, and C is thixotropic. So here they're saying that for C, let me write it here as C, okay, and come back to laser pointer. Okay, so once again, if you start loading, again the yield stress will be higher. So initially, when it's from rest to flow, the same amount of shear stress will be required to initiate the flow, but when it's unloading, the amount of yield stress to reach the rest state will be very less compared to the initial resistance to flow. I hope you guys have given some answer in chat box or polls. Let me see. Here someone has said, okay, B and D resemble same. You are speaking about question.
No, ma'am. The answer actually, if you say Bingham model, Bingham fluid, it is non-Newtonian. So first is Newtonian, that is confirmed. A is
Yeah.
Newtonian. Then B is non-Newtonian, as well as if you see the D option, it is Bingham fluid.
Yeah. But
And
exactly we
again,
have the name, not even rheopatic, thixotropic, all these are non-Newtonians. Except
huh,
Newtonian, everything is non-Newtonian. But if you have to pick the right answer, then uh, option D will be more appropriate, right?
why, ma'am? Because if it is a Bingham model, it's a non-Newtonian. So
But
B is
uh,
showing the characteristics of non-Newtonian as well
okay,
as shear
if I
thinning.
have an apple in my hand, if I have an option here, it's not a vegetable and it's apple. What will pick? You will pick apple, or it's not. It's not a vegetable. You will pick
But if you
apple.
see the answer B and D, ma'am, if you really read it very carefully, the first two
Yes,
options,
sir.
Newtonian
I'm
is
giving
okay.
an example. I put an apple in my hand. I'm asking to pick you out of two options. I'm saying not a vegetable and an option called fruit. What you will pick? Not a vegetable or fruit?
Obviously, ma'am, it will be fruit.
Yeah. So there are many. Even
But
not a vegetable is also right answer.
non-Newtonian is also not.
It's
Yes,
right
ma'am.
answer, but the right
So that's
one
why
will
I
will.
whenever
But the most appropriate one will be option B. So option D. Sorry. So you have to pick
ma'am,
option D.
when we are coming to the shear thinning, let us leave it the second part, ma'am. That is the non-Newtonian and the Bingham fluid.
Yeah.
If you see the third part, when C is satisfying more of shear thinning rather than thixotropic, ma'am.
Actually, it's they are saying fluid C mimics the behavior of fluid B when during the loading phase, but changes to a lower yield strength during the unloading phase, which
Ma'am.
means the yield strength will be high. Like once the material is at static, when during the loading phase, we'll put the material under shear, right?
Yes, ma'am.
So once it starts, so once we apply load, shear load, so the initial yield stress will be higher from rest to flow, right? From
Yes, ma'am.
static to flow, there will be will require some yield stress for the flow to initiate. But during the unloading phase of the shear, when we decrease the shear strain rate and come to zero, so while at zero you can see the yield stress starts decreasing. It does not follow the same path. But uh, if you take a Bingham model, here it's option B is nothing but Bingham model, Bingham fluid, right? So if you load it, it goes in the same linear relationship while unloading as well. But
No, ma'am. It's not about the confusion about the B part, ma'am. The C part. The C part, that
yeah,
is it shear thinning, or it is thixotropic? Because both the words are similar, ma'am. Because shear thinning, again, what you're showing the drawing as C, it during the yield stress, initial for both the thixotropic and the shear thinning, you require the initial yield stress, ma'am. Then only it will start mixing. Then only we'll be able to mix it.
yeah,
Then after loading, ma'am, now we see only the C curve. So shear thinning, that is what has been shown in the graph also in the earlier slide in number 3,
yeah.
the
Here
question
you're
number
saying
3.
right, shear thinning.
Shear thinning, that
Yeah,
is a pure curve, this thing.
yeah,
And thixotropic also follows the same concept, ma'am.
yeah.
Because if you take an example of sauce, because sauce is an example of thixotropic. So again, any thixotropic will not follow the same curve. It will again come in the dotted line what you have shown.
Yeah.
So how can we say that B or D, ma'am? That is the confusion what I had having,
Okay.
because rest of the things were okay.
Let me answer here. So when it comes to shear thinning, we are not speaking about the unloading phase. We are speaking only about the loading phase, right? With increase in shear strain rate, there will be decrease in the shear stress, right? That is shear thinning. Or else shear stress will not increase further here, right? Shear thinning. So during the loading phase, the shear stress tend to increase a little bit, but at a point it starts to be a flat region. The curve flats here, right? But we are here talking about the unloading phase as well.
Okay, ma'am.
So
In case of shear thinning, if we unload the train, ma'am, then what happens? It will also will it follow the same curve, or it will come back in the dotted lines, ma'am?
that we are not sure, right? There can be a material, an ideal material which can have follow the same path as well, right? We can't say all the shear thinning fluid should follow the same pattern, right?
Ma'am.
What you're saying is like, if you take a material like concrete and if you do it, yeah, obviously we can expect that. But we can't say all the shear thinning fluid should follow this thing. That is, they can be even lab produced material which will be shear thinning and follow the same loading same pattern. By loading and unloading, both will be same, right? It can be.
That's what the doubt is, ma'am.
But
Like,
only when it comes to shear
can,
thinning, it says that while when you increase the shear strain rate, there will be not much increase in the shear stress. It starts to increase a little bit, but further, but once it reaches a particular zone, it starts to flat. The curve starts to flat.
okay, ma'am. Till there, I understood.
It's
Once
shear
it is
thinning.
on the
If
loading
it's
part.
only if they have explained only up to this part, then it's shear thinning. But once they start about unloading, then you have to see whether we can. If they say about hysteresis and all, then you have to think about answering. So since they have told about the unloading phase as well, then it's better to go for thixotropic.
Okay, ma'am.
Thank you. So now let's see the next question. I hope you got it right.
Ma'am, got it, ma'am. Now I need to study more about the shear thinning part. If the unloading is done on the shear thinning elements of the material, then what is the characteristics?
Even
Whether
I
it
am
is
also not sure about the unloading part. How does unloading will be there in shear thinning material? I know I expect it to be thixotropic, but I'm not so sure.
ma'am.
Yeah, thank you. The correct answer is option D. A is Newtonian. Sorry, here coming. Yeah, Newtonian. B is Bingham fluid, and C is nothing but thixotropic. Okay. So now question 5, you guys have to give the answer in.
Before we go to this question, ma'am, the same related to this Bingham model and the Newtonian model, ma'am. Both of
Yeah.
them are linear in nature, ma'am.
Yeah.
So can we call this Herschel bulky model as non-linearly, ma'am?
Yeah, it's non-linear.
And
Both
both
shear
this
thinning and shear thickening can be represented
they are
using
non-linear,
Herschel-Buckel
ma'am.
model.
Yeah, especially this Hershey.
Herschel-Buckel model.
Yes, ma'am. That is also non-linear only, na, ma'am?
It's non-linear model. Yeah.
Okay, ma'am.
We have a question regarding Herschel-Buckel model. We'll see it after some time. Yeah. Now let's move to question 5. So question 5 is the match the following question. This is already given in the practice questions. I request everyone to give the answer in chat box. I have not launched this question in polls. So please give your answer in chat box. So let me start the timer now for 2 minutes. Okay. So here in the left side column, there are 3 options. One is cylindrical rheometer, second one is parallel plate rheometer, and third one is vane rheometer. All these are rheology measuring equipment, and then they have given 3 other options to match with the left side column. What is given in the left side column? So first one is spacing less than 1 meter between the walls. So usually while applying shear, we tend to give a very less gap between the two walls, two surfaces. So the material will be under poor shear. So the spacing less than 1 meter between the walls, and then one surface is stationary, and then can be used for mortar, which means cement mortar, because certain rheometers which is used in like uh, which is used to measure the rheology of asphalt or some other road building materials. Uh, no, they have adopted the model which is used to measure the viscosity of bitumen asphalt kind of materials. They have just adopted the method for cement paste as well, but which cannot be used to measure the rheology of cement concrete, because cement concrete has aggregates in it. So if the spacing is less than 1 mm between the walls, then obviously which cannot be used for cement mortars as well, right? So the minimum size of aggregate will be 4 point. So the sand size also, the maximum sand is 4.75 mm, right? So obviously which cannot be used for cement concrete. So still now mostly we use cement mortar. We have gone up to cement mortar to measure rheology. I have not heard about, maybe I'm not read recently about measuring rheology in cement concrete. I've read papers measuring rheology of cement paste, cement mortars, but not about cement concrete till date. I hope you guys have typed the answer already. Okay. 112233. Yeah, it's the right answer. Thank you, sir. Okay, now let's move to the solution part. So, coming to question 1, cylindrical rheometer. This is the diagram of cylindrical rheometer. Here you can see the radius from the central axis is nothing but 10 mm. The up to this inner wall till the outside wall, the radius is nothing but 10.85 mm. So, which means the difference is nothing but it's very less. It's about 0.85 mm. So the spacing between the two is less than 1 mm, that is 0.85 mm. So this is one of the example, but the sizes will vary, but overall the spacing will be less than 1 mm between the walls. Okay, coming to parallel plate rheometer, this is the representative diagram. This is from the lecture PPT. So here there will be two plates. One plate will be under station. One plate will be kept stationary, one surface, and then one more surface uh, will be under motion. So it will tend to shear the material in between the two plates, and then they'll measure the shear stress, shear strain rate. Okay. Coming to vane rheometer, so we have used this uh, vane shear apparatus for measuring the shear stress in clays, right, in soil geotech lab. So which can be used to measure uh, rheology for cement mortars. Okay. Now let's move to question 6. So question 6, let me read out the question and start the timer. So as explained in the lectures, the new design philosophy for cement concrete maximizes the aggregate composition to obtain minimum void space. I hope you guys have gone through the new design philosophy lectures. So in the lecture they have explained that the new design philosophy for cement concrete maximizes the aggregate composition to obtain minimum void space. Why we have to maintain minimum void space and maximize aggregate composition? Here we have given different options. So out of that you have to pick the right one. Let me start the timer and then please give your answer. Option A says that high paste content will be required to produce the desired workability. And option B says low paste content will be required to produce the desired workability. And option C says that paste content will not have any effect on workability. And option D is none of the above. Please give your answer in polls. I've launched this question already in polls. Time is up. Let's see your response. Okay, one more. I could see one more here person answering here. Option B, B, and A. Okay, let's see what's the right answer. And I have to check the polls as well, right? Here is question 6. Only one person has given the answer in polls. Okay. Okay. So here let me get back to the solution. So as per the new design philosophy, we have to combine three aspects here. So first we'll have to optimize the granular ingredients, because we have to do some sieve analysis, particle size distribution ranging from from the range of to the micro level, and then we have to optimize the granular ingredients to minimize the void space, and then paste content just enough to provide required workability. So if you minimize the void space, then the amount of paste content required will be very less to provide the desired workability, and then we can add more paste for better flow. Okay, for best flow. Okay. uh, the correct answer is option B, because based on the new design philosophy, we are maximizing the aggregate composition and minimize the void space as well, so that we need very less paste will be required to produce a desired workability, or else if there is more void space, then we need more paste to fill the voids, and then to produce a desired workability, we need more paste content. Okay, I hope you guys have given the right answer. Now I'm moving to question 7. This is a easy question. It's going to be either true or false. So let me read the question. The setting time of cement paste and cement concrete will be same in all the cases. Okay, here the question says setting time of cement paste. I hope you guys have done the setting time test in your BTech labs. So the setting time of cement paste and cement concrete will be same. I've started the timer. Is it true? Will the setting time of cement paste and cement concrete will be same? This is not from lecture PPT, but sir has discussed about this in the lectures when he was teaching fresh properties of concrete. If if you're given the answer, what is the minimum setting time for cement paste? What is the minimum required setting time for cement paste? Can someone say? What is the setting time for OPC cement paste? I hope you guys know the answer. Maybe you guys have typed in chat box. Okay. So the minimum setting time should be more than 30 minutes, and the final setting time should be less than 10 hours. There's nothing but 600 minutes. So let me see the class response now and then get to the solution. Okay, one vote says it's false. Yeah, it's true. Sorry, it's correct. It's false. So because setting time of cement concrete will be more than cement paste, because we are here the cement paste, the only material there is the cement paste and the water. So cement, we know that cement is reactive, it reacts with the water immediately and then it starts setting. So from initial 30 the initial setting time starts from 30 minutes, and it can happen anytime between 1 or 2 hours or 3 hours. Then the final setting time should be less than 10 hours. So the cement paste will set faster compared to cement concrete, because in cement concrete we add aggregates as well. So the amount of reacting material overall will be reduced, because in cement paste only cement and water will be there, but in cement concrete we add aggregates as well. So there IT set also comes to play. And then coming to question 8. So I've launched this question in polls as well. I've launched it as question 8A and question 8B. Okay, so question 8, let me read the question. So Herschel-Buckley model equation is given here. Tau is equal to, shear stress is equal to tau naught dash and then plus AR power B. Okay, so this tau dash tau naught dash and then A and B are material parameters. Okay, so this is the question. So in Bingham model, we have here the plastic viscosity. That's it. And then, but here we have some material parameters as well. So Herschel-Buckley model can be used to represent shear thickening and shear thinning concrete behavior based on the value of B. This particular value B, it's a material parameter. What does B less than 1 and B greater than 1 signify? I have launched this question as two questions, 8A and 8B. Please give your answer in polls or at least give your answer in chat box. You can type 8A and type the answer whether it's shear thickening or shear thinning. And coming to 8B, you can say whether the question, the given condition represents shear thickening or shear thinning. Let me start the timer for a minute now. If you're answering in polls, please answer for the two questions, 8A and 8B. In Herschel-Buckley model, we have a non-linear relationship between shear stress and shear strain rate. So here, based on the value of B, either the curve can be shear thinning curve or shear thickening curve. Time is up. Let's see the class response. Okay, B less than 1 signifies shear thinning. That's good. Yeah, B greater than 1 specifies shear thickening. Yeah. Let me end the poll for both the questions. Thank you. And then let me check the chat box as well. B less than 1 is thinning and B greater than 1 is thickening. Yeah, that's true. So here I've given, so if B is less than 1, it specifies shear thinning, and then B greater than 1 is nothing but shear thickening. So here I've given I've taken a snap from web directly, and then it's a x-axis nothing but shear strain rate and y-axis nothing but shear stress. So here we know that if there is a linear relationship and if it has initial yield stress, it's nothing but Bingham model linear stress strain relationship. But when it comes to shear thinning, then the n value will be less than 1, and when it comes to shear thickening, the n value will be greater than, sorry, here it's given as n, but here whatever parameters I have given is nothing but B will be greater than 1 for shear thickening, and then B will be less than 1 for shear thinning. Okay, now let's get to question 9. So here it's a true or false question. It's going to be an easy question. Let me start the timer now. It's a direct question from the lecture. The statement is the diameter of the pipe used for concrete pumping should be at least 3 times the maximum size of aggregate. That is the question. Here they're saying if the size of the aggregate is 1 mm, then the diameter of the pipe should be at least more than 3 mm. That's what they specify. The diameter of the pipe should be at least 3 times more than the maximum size of the aggregate. It's true or false. You can give your answer in polls or you can give the answer in chat box. We have only one more question to answer, then we can leave the class. It's already 7, but I won't take more than 1 or 2 minutes for 10th question. And if you have any query, please be in the class. We will discuss and then we can leave. Okay, I hope you guys have given the answer. Okay, true. True, okay, yeah. Let's see if you guys, someone have given the answer in polls as well. Yeah. Thank you. Let me end the poll. And still we have, I've launched question 10 as 10A and 10B, like similar to the previous question. So already you guys have given the answer. Okay, that's fine. if someone let me discuss the question once again here. So this question, coming to question 9 solution. So it's a direct question. Here from the lecture PPT, they say that the pipe diameter should be at least 3 times the maximum aggregate size. So, and we should avoid using large aggregates because it tend to block near the bends, and even while pumping its way, we have to give more pressure for large aggregates to move. So, coming to question 10. So let me read out the question first. Slump flow test is used to measure the workability of self-compacting concrete. I'm not saying about the conventional slump test. I'm talking about slump flow test. Okay, so slump flow test is used to measure the workability of self-compacting concrete. Slump flow test measures. I'm giving here two parameters measured. One is overall spread. Once you fill the slump cone with flowable concrete, okay, we'll measure the overall spread, how much it will spread. Usually self-compacting concretes will spread from 700 to 800 mm. If it's a high flow self-compacting concrete, it will spread up even up to 800 mm. And then the time to spread 500 mm. So we'll start the timer once we lift the slump cone, and then we'll measure from its rest to how much time it required to reach the 500 mm dia. Okay, so overall spread will be even up to 600, 700, 800 mm. But what is the time required to reach the 500 mm first? So there will be a marking in the it will be a very flat board or a flat surface. Over that we'll mark it with chalk piece, or there will be marking in the board itself till 500 mm. So we'll start the timer once we lift the slump cone, and then we'll measure the time till how much time does it require to reach the 500 mm. So we have to identify the indirect findings from the slump flow test results. So this is not directly from the lecture PPT, but sir has explained this in the lecture videos. So if you have watched the videos, you will be able to answer this question. So you have to find the indirect findings from the slump flow test results. So from question 10A, you have to find what does overall spread refer to. Does it refer to the yield stress or viscosity? And option B says the time to spread 500 mm. What does it refer to? Whether it refer to the yield stress or viscosity. Okay. Now let me start the timer for a minute. Please give your answer in chat box or polls. If you are answering in the chat box, please write 10A whether it's yield stress or viscosity, and 10B whether it's referred to yield stress or viscosity. This is the last question. Time is up. Let me see your response. Okay. Overall spread refers to yield stress, and time to spread is nothing but viscosity. Yield stress and viscosity. Okay. Let's see the okay, let me check the polls as well. Okay. Now let's see the solution. Leave the class now. So here is one of the snap from the lectures. So we'll measure the overall spread, and I personally have worked in a project when I was working in a research project. So we were working with different combinations of cement with limestone and fly ash, So when we tried to, and we are using Portland pozzolana cement, and in that even we tried to replace some fly ash and some limestone. The strength was very minimal. We got only up to M5 to M10. That was our strength target. But the flow we required was around 800 mm. So we didn't concentrate on strength, but majorly on the flow of the cement concrete. So when we are doing the test, we are able to achieve around 700 to 800 mm flow, and then we also measure the time required once we lift this slump cone, and then what is the time required to reach the D500 mm. So initially we didn't do the test, then our professor recommended to measure the time what is required from 5 to reach 500 mm. So we also did V funnel test, in which we also measure the flow required for all the concrete to flow through the V funnel. If you have gone through the lecture video, then obviously you guys know what is V funnel test. So what is the time required? So from that we'll differentiate what is the type of the flow of the concrete. So from that we did this test, and I could remember that now as well. So here the overall spread is nothing but the minimum, it's measuring from rest to flow, right? So it measures the initial resistance to flow. So while taking it from rest to flow, the liquid will have some initial resistance to flow. So from there we can refer it as yield stress, and from the overall spread we'll get to know how much it is able to flow. So it is nothing but the yield stress measurement. And coming to option B, so we are measuring the time. So in the time, so what we are able to see is while flowing, what is the resistance to flow. If it takes more time to flow, then we are saying it has more resistance while flowing. And if it reaches 500 mm very fast, so we can say it does not have much resistance to flow. Just think about a water flowing out of the slump cone. It does not have, it will flow immediately in 1 or even less than a second. It will reach 500 mm, right? So from here we can say that overall spread refers to yield stress, and then time to reach 500 mm reach to viscosity. And I have to say here one thing: even if the concrete is easily flowing and does not show any resistance to flow, there is more chances for bleeding as well. So in our case, we does not want even the concrete to flow fast from to reach 800 or 900 mm. So we need the concrete to flow slow and steady and reach that 800 mm. So then only there will be not any segregation uh, or bleeding to happen while flowing through complex structures or complex geometries while while placing the concrete. So that was one of my learning here. So we does not want concrete which has very less resistance to flow. We need proper with optimized resistance such that it will reach the and it has to reach that 800 mm as well. Then only it will not face any bleeding or segregation while flowing. Okay, I hope you guys find it useful for submitting the assignments. So
Ma'am, one small doubt, ma'am.
yeah.
Does this paste, ma'am, increase the viscosity of the concrete, ma'am, or decrease the viscosity?
Sir, the paste content, whatever we have, it's going to be a very fine material, right?
Yes, ma'am.
Obviously, it will increase the viscosity. Paste
Okay, ma'am.
content, coming to paste content alone, it will increase the, if you increase the paste content, it will increase the viscosity.
Okay, ma'am.
Yeah.
Then
And we
how
need
about the
enough,
yield stress, ma'am?
yeah.
With respect to yield stress, ma'am, will it decrease or increase, ma'am?
Uh, like if we
If
have
we are
more
increasing the
core,
viscosity, which is
yeah,
on the x axis,
yeah,
if we are increasing that one graph where sir showed that more paste, that is self compacting concrete, we increase more
yeah,
paste,
yeah, yeah,
so
yeah,
the viscosity will increase.
yeah.
So in that, can we say that the yield stress decreases?
Yeah, the yield stress will decrease because when it comes to yield stress particularly, if there is more coarse aggregate and we need some fine material in between to fill the voids and initiate the flow, right?
Yes, ma'am. So
So
for
if we
that
have
only,
more coarse aggregates, then we need more initial stress to initiate the flow.
yes, ma'am, that's true.
Yeah,
But if I'm increasing the paste, I'm filling all the gaps, and my content of cement paste, that is slurry, is getting more
yeah,
as compared to aggregate. So can I say that my viscosity will increase and the yield stress will decrease
yeah,
or increase?
yeah. Viscosity will increase, but yield stress will decrease.
Okay, ma'am.
Yeah,
And in one of the slide, ma'am, actually there was a small correction, ma'am. It's really sorry to pinpoint that,
yeah,
but
it's fine.
It
Tell
is
me.
the requirement of pumped concrete, ma'am. In after I think tomorrow might be the session because last Tuesday also there was no session. Not in your slide, ma'am. What professor was teaching, ma'am. In that
Okay.
it is shown as 1000, ma'am. 1000 mm to 150 mm, whereas it has to be 100 mm to 150 mm.
Okay. Probably they would have corrected in the lecture PPT,
No,
but
ma'am. Even in the talk, generally, sir, sometimes he says that this is a old figure and this needs correction and everything. But in that particular slide, there was no correction in the theory also.
oh, in the lecture PPT also it was not corrected.
No, ma'am.
Okay,
So
let me try to correct it at least for the next time. We'll
uh,
try to upload it right.
it is requirement of pumped concrete, ma'am. The slide heading is
Yeah,
requirement of
100
pumped.
to 150 mm slump, right?
Yes, ma'am.
Okay.
It is showing as 1000 to 150.
Okay. We'll try to change it. Thank you. Sir, in the last session, you were asking about mm, the mark distribution, right?
Regarding those four, if three are right and two
Yeah,
are that thing, ma'am.
yeah,
Yes, ma'am.
yeah.
I just left it, ma'am. After that, for the there's nothing
Sir,
about the mark.
actually, we are actually configuring the assignments every week. So while we try to give the answers, it is giving mark for us. But I don't know why you didn't get any mark. Can you reply in that case for what particular questions? For saying it for one or two examples, can you just type? You have just posted the question discussion forum. Just below it, you just type what are the one or two questions which you had faced problem.
I'll
Uh,
just check, ma'am, because to be very frank, ma'am, I am also pursuing my PhD, so I'm very, very busy with all my
okay,
office work as well as studying, ma'am. So in
okay,
the
sir.
whole night I have to study. I'll see, ma'am, if I can trace my assignments and get the answers.
Yeah. Okay. Thank you. Thank you all. Let me wind up the class here. Thank you for being patient and giving your answers. Thank you.